Hello and welcome to another MuSkeMo tutorial. This is Pasha van Beidert speaking. In this tutorial, I'm going to construct the emu model you can see right now, starting from only bone meshes and meshes representing the tissue outlines. This is going to be a rather comprehensive tutorial demonstrating most of MuSkeMo's panels and features, although not all of them. And I'll also be demonstrating many MuSkeMo and Blender tips and tricks along the way. So because the tutorial is going to be rather long, I'll be adding timestamps after uploading. Hopefully this will help you to navigate through it more quickly if you're just looking for how a specific feature works. Users familiar with my research might recognize this model. It quite resembles the model I constructed for this publication, as you can see here. The actual model has more muscles than we're going to add in this tutorial, and you can see here that for this visualization I used the volumetric muscles visualization, and here we're just using the basic tube visualizations. For this tutorial, I'm going to assume that you've downloaded and installed both Blender and MuSkeMo and that you are somewhat familiar with the interface of both. I have tutorials on both of those topics as well. Just like in the previous tutorials, there will be a keyboard and a mouse on screen which allows you to see what buttons I'm pressing. That will hopefully help you follow along, although I'll try to call out what I'm pressing as I'm pressing it during the tutorial as well. And for this tutorial, we're also going to start by downloading the sample dataset from Github. So you should go to the MuSkeMo GitHub, to the releases page, and download MuSkeMo sample dataset 1, which is this zip over here. So in Blender, we can open a new scene, delete the default cube, and let's save this so that if a crash happens, which is not necessarily likely, but if it does, then we will have we'll have saved our data. So that's just good practice to do. Tutorial 3.blend and save. So we want to import our 3D meshes, scans, etc. and use MuSkeMo to start constructing our model. So let's import some scans. We're going to import OBJs because the bone files are in OBJ. The emu data is in the emu folder, obviously, and we're going to press emu geometry, then select 1 and hit A. This selects the entire folder, and we want to hit split by object. We want to turn this off. And if we import it just like this, you might not notice, but I noticed because I built this model, that actually Blender has rotated the entire model. The Z-axis is the up direction, whereas I constructed the model and exported the files with Y as the up direction. So by default, Blender rotates your objects during import. This is quite strange. You can see this in the rotation panel as well. Everything has been rotated about the X-axis by 90 degrees. So let's undo this. We could just rotate everything back manually, but we're not going to do that. Instead, we undo everything, import OBJ again, and we're going to change the forward axis to Y and the up axis to Z. And with these settings, MuSkeMo does not rotate your files. So we select everything again, hit import wavefront OBJ, and now our file is correctly imported. Now you will notice that the left side doesn't appear to have a femur. I'm going to fix this after uploading, after recording this tutorial, but for this tutorial actually this won't matter because we're only going to be constructing a right side and then use the reflection panel in MuSkeMo to construct a left side. So I've selected them and just hit delete. So for a model, you will need all of your bone meshes to be individually selectable, and you want them aligned or you want them arranged in some physiological or neutral posture. in Blender, you can simply select the meshes and use G to grab them, G to move them. G stands for grab, and you can hit R to rotate them. By default, Blender rotates about the origin, and that's not always what you want. So you can, for instance, rotate about the 3D cursor, and the 3D cursor is this strange little thing over here. If you hit Shift and then right mouse button, you can change the location of the 3D cursor. So if I hit Shift right mouse button, now I'm rotating about that point. So this is just something you will need to familiarize yourself with, but then you can arrange your bone meshes in whatever starting posture you like. If your bone meshes aren't individually separable, for instance, like these toes, I've turned them into one single mesh. But if you still have a segmented scan where the bones aren't individually separable, you could potentially fix this in Blender if you like by going into edit mode. So you hit Tab on the keyboard. Now you're in edit mode, and you can see that suddenly you can select individual vertices. Vertices are these little dots. I prefer going into face selection mode. That is this button over here. Then you can select the actual triangular faces of your mesh. If you hit this button, you go into X-ray mode. Then you can select entire sections of your mesh that you might want to split off. Then hit P for separate, and then hit separate by selection. Now these bones are individually selectable. So if you haven't already done this, you will have to go through all of this. But for this tutorial, that's not necessary. So I'm going to undo what I just did. And now I have my bone meshes. I want to arrange them in a collection, which is just a folder that's easier to work with. So I hit right click, create new collection. I'm going to call these bone meshes. We select everything in the viewport, and then we can just click and drag and move them into that collection, and we can collapse this so it's slightly easier to see what's going on. So now we have our bone meshes, but I also want some tissue outlines. I want to assign masses to each of these body parts. So I'm going to again import my tissue meshes. Now these might be, for instance, CT tissue outlines that you've segmented. I'm going to import convex hulls, which are also created with MuSkeMo, but the principle is essentially the same. So I'm going to import these as STLs this time. In the same folder, we have MuSkeMo skin outlines.stl. The forward axis is now correct, so we can just hit import STL. And now we have this nice little mesh. This is correctly aligned with the skeleton that's underneath. So we don't have to do any rotations. But it immediately imported it into the bone meshes folder, which is not necessarily what we want. I'm going to create a new collection and call this skin outlines and move them in there. So with these collections, if you hit this eye icon over here, you can hide the collection, everything that's in the collection, and then you can select what's underneath. Now bear in mind that if you don't do this and you select something, you're also selecting things that are underneath the object in question. So if I now turn this off, you'll see that I'll have accidentally selected the bones. You have to be mindful with what you're selecting, and if you're worried about this, you can turn X-ray mode on, which is this button over here, but that doesn't always make things easier to see. So I'll leave this off. And what we want with these skin outlines, we're running into the problem that I was talking about earlier. These meshes are not individually selectable. So to remedy this, I'm going to hit Tab to go into edit mode, hit A to select all of the faces in this mesh, then again hit P, and this time separate by loose parts. This turns the combined mesh into each of its component parts. Now bear in mind that this only works because the mesh that I made is actually consists of separate individual meshes that are all watertight and triangulated, or at least they're all watertight and individual meshes. If you have one combined mesh from a segmentation, then you cannot separate it like this. But for the EMU mesh, it will work. We want to essentially assign a density to each of these skin outline meshes so that we can compute the inertial properties, assuming constant density. So we're going to do that in the inertial properties panel. And there's several ways that this panel actually works. The easiest way is to just assign a specific collection. In this case, it's the skin outlines collection. I'm happy with a segment density of 1000, which is equal to water, and just say compute for all meshes in collection. And then hit compute for all meshes in collection. It took a second, but it has now computed the inertial properties for all of the objects in the skin outlines collection. And we can see that here, because now, for instance, this selected mesh, if I go into the custom properties, remember that's under the object properties, we can see that it has a center of mass, a density, an inertia about the center of mass, and it has a mass. Now there's other ways that you can do this. You can also select specific meshes and then hit the button compute for selected meshes. And you can also, of course, change the density. So if I select this one, and because this represents the skin around the rib cage, we might want to give this a lower density because of the lungs and the air sacs in this animal. Maybe we can give it a density of 750. I hit compute for selected meshes, and you'll see that the mass has gone down. Bear in mind that this will only work for meshes that are watertight and are triangulated. So MuSkeMo will warn you if this is not the case. So for instance, if your mesh has a hole like this, and I try to compute it, then you'll see that it doesn't work. You'll have to fix this mesh first. You'll have to fix all of the holes in this mesh. So if we undo this, you'll have to fix the holes in this mesh. The only issue is that your mesh is not triangulated. So for instance, this cube here, if I want to compute the inertial properties, it will say that it's not triangular. This is easy to fix. You just go into tab, select all, and then under faces, hit triangulate faces. Now you can see that they're no longer squares, but they're triangles. Now I can compute the inertial properties, and you'll see here that this cube would weigh 6,000 kilos if its density was 750 kilograms per cubic meter. Bear in mind, MuSkeMo assumes your meshes are in meters, so you should ensure that the scale of your objects is correct, and if they are not correct, you should scale your object and then hit Control A, which stands for apply, and then apply the scale. Because the scale, if you select your object in the transform panel under item, should be 1 across the board. If it is, for instance, like this, and you have a number over here that's not 1, then MuSkeMo might give you issues with non-realistic dimensions. Okay, so now all of these objects have inertial properties. That's great. We can start creating our first bodies. To do this, let's hide the skin outlines for a second. I'm going to create a body. Let's call our first body the pelvis hat body. So in MuSkeMo, we go to the body panel and we type in the desired body name. So this is going to be pelvis and then hat, which stands for head, arms, and torso. This is going to be a composite body. if you want, you can change the display size, which in this case I think is going to be fine for this emu. And then I just hit create new body. And you will see that a new body appeared here and a new collection has been created, which is the bodies collection. So I could manually start changing things here, but you should really never do this unless you really know what you're doing. What we're going to do is assign inertial properties to this body over here. So let's turn X-ray on for a second so that we can see what we're doing. I want this body to represent the combined inertial properties of this mesh, probably I'm going to turn the bone meshes off, probably everything that's to the front here. So I select all of the target meshes for which I have inertial properties computed. I select the target body, which is selected, and then I just hit assign pre-computed inertial properties. Now MuSkeMo will tell you how many of the meshes you have selected have pre-computed inertial properties, which in this case is 27. Now we hit assign pre-computed inertial properties, and you can see that the body that we created has jumped forward. That is because bodies are always placed at their global center of mass position in the global reference frame. So this body is now placed at its center of mass. You can see that it now also has mass, so it has the combined mass of all of these objects over here. And it has the combined center of mass of all of those skin outlines. So we can hide these now because we don't need them anymore. So I'm going to select them and then hit H to hide. If you want to unhide them, they're still here, but you can see that their individual eye buttons have actually been toggled. So they're all hidden now because we don't need them. I computed these inertial properties from convex hulls, which were also created in the inertial properties panel by MuSkeMo. But I'm not going to go over that in this tutorial. I'm going to create a separate tutorial for that. But the principle is the same if these meshes, if you compute the inertial properties from tissue outline meshes that you segmented from CTs. So for the thigh R body, I want to use the respective skin outline for the thigh. Now, maybe I didn't point this out already. The body panel shows you which bodies you have selected. So in this case, I have the thigh R selected. If I select this one as well, we have two bodies selected, and then you get the counter over here. I want to select, again, the thigh R body and the skin. So we hit assign I select them both. I hit assign pre-computed inertial properties, and then the thigh R body flipped to its center of mass. Perfect. I'm going to repeat the process for these segments, so I'm going to just speed up the video. So through the magic of editing, I have added a thigh R body, a shank R body, a TMT R body, and a toes R body. I'm adding the suffix of underscore and then lowercase r to signify that it's a right side. Now this is my preference, but you have to be consistent with your choice if you want the reflection panel to work, and by default the reflection panel will use lowercase r as the suffix to denote the right side. So unless you have a strong preference for something else, I recommend you use this as the same convention. It's going to make reflecting objects easier later on. So we've created these bodies, but they're not actually attached to each other nor to the bone meshes yet. It's the bodies that give the inertial properties of the model, but the meshes, the bone meshes, they're there for visualization and will also help us figure out where we want to add joints and add muscles, etc. So we can parent them to the bodies. This happens in the body panel, and it's quite simple. You open the Attach Visual Bone Geometry subpanel. You select a body and one or more meshes that you would like to parent, and you hit Attach Visual Bone Geometry. Now, you will get a warning over here, and it said that the geometry folder doesn't exist yet, and so it has been created. If I now select the thigh, you will see that the femur moves together with the thigh. I haven't done this for the shank yet, so if I do the same for the shank, you will see that I can move the shank without moving the actual shank bone geometry. In parenting these to each other, the thigh R bones were moved to the geometry folder. So by default, this is called geometry. In the EMU model, this was called EMU geometry, but there's no real need to change the default setting. This is also what the folder name will be if you export a geometry folder. So that's why I prefer giving them more specific names, but geometry will be fine. So we have to do this for all of the bodies. So the pelvis hat body has this big mesh as its visual mesh, but also all of these. So all of the neck geometries, and then we just again hit Attach Visual Bone Geometry. And now if I select that body, we will see that this entire section moves along with it. It's also possible to do it in reverse. If I select this geometry, I can detach it, and now only the distal bits are attached to that body. So I'm going to quickly attach it again, and there we go. Now we do the same for the shank. Attach. For the metatarsus, attach. And for the toes. Now we are ready to start adding joints. So there's two ways to do this in MuSkeMo. Both of them require you first, of course, to create the target joint. So instead of starting with a hip joint, I'm going to start with the knee joint for now. So the simplest way is to just do it like this. We type in a name, again with a side string at the end. So this is going to be a knee R. We create the joint, and it ends up over there. And actually, this looks rather big, so I'm going to undo this and then make the visualization radius slightly smaller. I'm going to redo it. So now we have a joint, and it is as simple as simply aligning the object in 3D space. The neatest way to do this is to go to the principal direction. So if you hit 7, you are looking along the Z-axis. We align it here, approximately where we want it. Maybe just over there. No, over there. That's fine for this tutorial. And then we hit 3 to get a front view. And then I am going to hit Z, so I can only move along this axis, and I'm going to place it here. So that's one way to do it. You can simply do it manually. And then to turn this into an actual joint, we first select a parent body, which is going to be the thigh, and then I select the joint. And once again, you can see that the panel tells you that you've selected the knee R joint, and you've selected one body, namely the thigh R body. Then you can hit Assign Parent Body. Perfect. Now, if I move the thigh body around, you will see that the joint is moving around with the body. And to assign a child body, it's as simple as simply selecting both. You will see the knee R and the shank R body are selected. Then you just hit Assign Child Body. Now, if I move the joint around, you will see, for instance, by rotating about the global Z, you will see that the shank is moving about the femur. Perfect. So there's more than one way to define the joint. This was the easiest way. You simply assign it manually. If you're not happy with the exact placement, you'll have to unparent it and then redo it. But there's a different way to assign joints as well, and I'm going to demonstrate that with the femur, because you're able to do primitive object fitting in MuSkeMo. So I'm going to select the femur and then hit slash. So now we go into like an isolated view where we're only viewing the femur. And what I want to do is fit a sphere to the head of the femur. And then I'm going to use that as the joint center for the hip joint. I just hit tab to go into edit mode. Then I'm going to turn on. By the way, if you don't like this square selection in edit mode, you can also go for lasso selection. So you hit this, hold down the mouse button, and then select lasso. And then you get something like this if you hit shift. Now I want to select the entire head of the femur. So what I'm going to do is, again, hit X-ray. And you can see that because it's a CT-based mesh, we have some internal geometry as well, which I don't want to be selecting. So in this case, I'm actually going to go out of X-ray selection and just make sure I select enough visually. Here we go. And select this and maybe get rid of some of this. So if you want to deselect something, you hold down Control and do the same thing. And selections can be undone, which is quite useful, and they can be redone by hitting Control Shift Z. There we go. Okay, so we have this bit selected. What I'm going to do, what we actually want to do is duplicate this and split it off into a separate mesh. So we hit Shift D, that duplicates it, and we hit Escape. If I move this around, I displace it, which I don't want. So I hit Escape. It's there, and with this selected, while it remains selected, we hit P like we did before, and then hit Separate by Selection. Now we go out of edit mode, and we now have this separate piece of geometry, which is, by the way, parented to the thigh R body. So we don't want that. We're going to detach visual bone geometry. So it's no longer parented, and we're going to move this out of the collection because this is essentially the femoral head. Now once we've done this, we can hit slash, so we go out of that selection mode. Actually, let's stay in the selection mode. So I hit slash again, and what I want to do is fit a sphere to this, because this seems approximately sphere shape, so that will hopefully work. So to do this, we go into Joint Utilities, and with the object selected, we hit Fit a Sphere. And it doesn't really matter which one you pick, they'll both give the same result. And there we go. Now we have fit a sphere to the femoral head. And this is going to give us our joint center position. So let's create a new joint. Hip R, create new joint. It's at the origin, and we would like it to be aligned to this fit geometry that we've created. I have a button for this, and that button is called the Match Position button. You have to select both one joint, and as we can see, we have selected one joint, that's the hip R joint, and we have to select a source object, which in this case is the geometric fit sphere. So we go Match Position, and there it is. Now our hip R joint is in the correct position. So now we have this joint. We we'll once again want to parent it. So we select the joint, select its parent body, which will be the pelvis hat body. I can close this. And then we say assign parent body. If I make a mistake, let's say I select the joint and want the thigh R body to be its child, and instead I select the thigh R visual mesh and I hit assign child body, we'll get an error. MuSkeMo tells you if you're doing things incorrectly. So if you read the error, you can usually tell what you have to do. So it just told us to select a child body instead. So now we hit child body, and now we have a hip joint. Perfect. We can do the same thing for the shank joint, and I think I will do that just to demonstrate one thing you might run into. Through the magic of editing, you will see me quickly add a cylinder fit here. So with that selected, I'm going to detach this visual bone geometry again. So we've detached it, and now we can fit a new geometry, and we'll be fitting a cylinder. So I've got it selected, I hit fit cylinder, and there we go. We now have a nice cylinder object to which we can fit our joint. And in this case, we got lucky. If I have it selected, it looks like the y-axis is pretty much aligned with our global axis. And this is not always the case. So sometimes you will fit an object and then the cylinder will be, for instance, oriented like this. This is not necessarily a problem, right? Because we can create a new joint, which I will do. I'll leave this open actually. We can create a new joint. This is going to be our ankle joint. Ankle R. Create new joint. It appears at the origin, but it might be easier to select it here. There's our ankle joint. I select the cylinder fit and I hit match position. We can also match orientations, which sometimes is useful. But in this case, let's say our cylinder has a strange orientation, but we only notice this after we assign the shank R body as the parent body. Now if we move the shank around, the ankle moves along with it, and then after matching the orientation, let me hide this. We notice that our joint is not aligned in the way that we would like. The local x-axis of the joint is flying off in backwards direction, and that's not nice. So we've already parented it to the shank. If I now rotate this joint back, remove all of the orientations, so I set all of these to 0 in the item panel. I clicked item, and then in rotation I'm setting all of these to 0. Now I have everything aligned as I want. But if I now assign a child body in MuSkeMo, I can hit assign child body, and now we get an error. It says that you're attempting to assign a child body to ankle R, but the joint is not in its default pose. So it's not allowing you to parent this. And essentially what happened is the joint was in this orientation when it was parented to the shank R body. And after that, we changed its orientation and tried to assign a child body. And then MuSkeMo throws an error because you're not allowed to change the location of things after they are parented. The reason for this is that the inertial properties of the bodies are computed in a certain position. Once you move these around, the center of mass of the bodies will be out of date. So to prevent this, MuSkeMo does not allow you to move things around after you compute them, or it asks you to recompute them in the new current position. So in this case, this joint was rotated, and probably we don't want this rotation. So what we can do, we can clear the parent body, we can remove the rotation. So we set all of these to 0. Now it's aligned with the global reference frame. And now we can assign a parent body, and we can assign a child body. And now I did something strange again, and I get another error. I tried to assign the shankar as both the parent and the child body. That's not allowed, obviously. That would lead to a recursive model. So I select the correct child body, I hit assign child body. Now we have an ankle joint that was also created using a fit cylinder. Let's quickly create an MTPR joint, so a metatarsophalangeal joint. So now we have all of the joints that we might like to add. One more that is worth adding is maybe a groundPelvis joint. That is essentially what's going to decide the global degrees of freedom of the body. I like to call this a groundPelvis joint, but I think that might be an OpenSim convention. Some people might call them free joints or parent them to the world body if, for instance, you're building a MuJoko joint. The way that we're going to do this is create a new joint, create new joint, and it ends up over there, which actually it doesn't really matter where we place this, so we might as well leave it here. Sometimes I put them in the same XY position as the hip joints on both sides. So sometimes I put my pelvis joint in between the hip joints, because then hip height is the same as the pelvis height of the model, which is useful for some of the computations. Actually, I might do that now as well. So the hip joint has this X location, so we just copy it to the groundPelvis joint, and the hip joint has this Y location, so we copy this to the Y. And then we select the groundPelvis joint, select the pelvis hat joint, and assign it as a child body. Now, if I select the groundPelvis joint, the entire model will move. And that is what we want. If a joint is intended to be the global degree or a global degree of freedom for the entire model, then the parent body is essentially the ground. You can type that in manually here if you like, but it's not required because the OpenSim conversion MATLAB script that I've created will deal with this automatically. But if I export this model and want to turn it into for instance, an OpenSim model, then I want to at least define what axes I want as joint coordinates. For instance, the hip joint, I might want the local Z to be defined as the hip angle. So I can do this in the joint panel, and we go to joint coordinate names. With the hip R selected, I might call the hip angle R. Then we hit update coordinate names, and you should see here that hip angle R is now one of the coordinates. This panel, this is essentially all it does, so you could type these in manually over here. This is one of the few things where typing things manually won't really have a big difference. The only thing that this will do is during model conversion, you are telling MuSkeMo that you want this to become a mobile degree of freedom. All of the other degrees of freedom, so Rx, Ry, and all of the translational degrees of freedom, will be locked. Those will not be degrees of freedom during model conversion. So for the GroundPelvis, we want a pelvis tilt, pelvis, sorry, I accidentally hit the number pad here, pelvis TX, and a pelvis TY. Then we hit update coordinate names, and now they've shown up on the right. For the knee, I'm going to call this knee angle R. Delete this, update coordinate name, ankle angle R for the ankle, and MTP angle R for the MTP. And there we have it. Now our joints have coordinates for if we ever decide to convert this model to using MuSkeMo's conversion scripts. That's all we want to do for the joints. Next up is creating muscles. This, of course, happens in the muscle panel. And you will see here at the top that you cannot create muscles unless at least bodies are created. It is in principle not necessary to create joints, but bodies must be created. And remember that you can only later on export all of your model data as long as everything is still in the pose that it was constructed. Let me first remind you how to change the position of the 3D cursor. So the 3D cursor is this weird little thing over here. And there's two ways that you can change the position of the 3D cursor. One is simply by hitting Shift right click, and then the 3D cursor is projected onto whatever surface you have placed it. So that is one way. The other way is by selecting this, and now the 3D cursor will be hit by left clicks, but now you can't select anything. Now you actively move the 3D cursor. So I prefer having this selected and then hitting Shift right click. So muscle points are added first by creating a muscle. To create a muscle or adding a muscle, you always need to have a body selected and the 3D cursor in the position that you would like it to be. So let's create a muscle, and we're going to call this muscle iliotibialis cranialis. This is a muscle that emus have, and I'm not going to type out the entire thing. I'm going to call this IC and then R for the side. So it's the right side. And I'm going to create the muscle, and I got an error. I forgot to select the parent body. So this is important. You have to select a parent body, otherwise the muscle point would float in 3D space. So I want this to be parented to the pelvis, which is part of the pelvis hat body. So we select that body and we do create new muscle, and there it is. That's our new muscle point. The muscle has, of course, been added to the muscle collection. It's only a single point, and you might be tempted to reposition it by selecting it, as I'm doing now, and hitting G, and then you'll see that you can't actually reposition anything. The muscle stays in the same point, and that is because muscles are curves, and you can only change their position in edit mode. I'm going to add another point, and then it'll be easier to see what I mean. So the next point of this muscle, I'm going to add to the distal femur. So I'm going to add it there. Select the thigh R body. And then I'm going to not create a new muscle, but I'm going to add a muscle point. If I hit create new muscle, it'll tell me that I forgot to add a name. But it does know that I have the ICR and the thigh R selected, so I can add a new muscle point, which I've now done. And you can see that, well, that's not exactly where I wanted this muscle point to end up. It's just simply that's where the 3D cursor was projected when I hit Shift right click. So what I have to do to reposition this muscle point is to select the muscle, and again, if I hit G, I can't move it, but if I hit Tab to go into edit mode, the individual points become selectable, and these ones I can move. So I can either use this gizmo that I have turned on, or if you don't like that, you can hit G and then X and move it forward a bit. I think that looks okay. And this muscle, the iliotibialis cranialis, it inserts onto a big combined tendon of many muscles, but we're just going to pretend that it inserts perfectly onto that bone. So currently, this point is attached to the femur. So if I rotate the knee, nothing happens. But if I rotate the hip, then obviously it will rotate along with it. I wanted to attach the shank as well, so we put the 3D cursor there, select the target body, select the muscle in question, and then we hit add muscle point. And now it tells me I have too many objects selected. That's strange. Oh right, I still have the joint selected. So we deselect the joint. I'm hitting Control and then dragging with the left mouse button. Then we do add muscle point, and now we have an added muscle point. Now this looks a bit weird in this posture, but actually an emu cannot extend its knee this far. So in a more realistic posture, you get something like this. And it is of course possible to either play with these points more or add wrapping, which I'm not going to do for this muscle because this is just a demo tutorial. So let's add a few more muscles. So now we have a nice hip extensor muscle. Actually, this might be a bit too high up. So if we want to move these points around, again, hit Tab and go into edit mode. And I might want to move it here. But now you will see that if I move this, it's not projecting onto the bone surface. And that's something I actually would want. So to be able to do that, we hit Snap, and then by default, snapping is set to increment, but we want to snap to face. So now that snapping is enabled, if I again hit G with that point selected in edit mode, now it's snapping to the bone surface, as you can see. Perfect. Okay, let's add another muscle. This is going to be a hip flexor and a knee flexor muscle. And let's select the shank, our body, and the muscle in question, and then hit add muscle point. And now we see something that we might not be happy with. The muscle is a straight shot, and it's going through the bones and it's going through other muscles. So to insert a muscle point, we first look at where we want it. Well, we have point 1 and we have point 2, and I want it after point 1. So that's actually what the panel assumes by default, insert after point 1, and the rest of the panel works the same. So you have to select the index after which you want to insert, but afterwards you just place the 3D cursor where you like, for instance there, and then you have to select a parent body. Now, up till now I've just been placing points and then moving them afterwards, which you can do, but you can also move the 3D cursor to the exact location where you want it, which you can do via the view panel. There it is. In the view panel, you can see the 3D cursor location, and you can play around with it. So that's where I want the 3D cursor. That's where I want to add my new muscle point. I have the correct body selected, the pelvis hat body, and I just hit insert muscle point. Then it says that I forgot to select the muscle. Of course I did. So I also select the muscle, insert muscle point, and there it is. This is how you insert extra points in MuSkeMo. If I then want to modify this further, I can go hit tab for edit mode, select the specific point, and then can move it around at will. So in this case, it's kind of hard to see what the exact point of the muscle is because it's so wide, so we can change this by going into the modifier panel, that's this wrench while we have the muscle selected, and then scrolling down until we come to the simple muscle visualization node. This is a geometry node that essentially creates this visualization. If we turn it off, the muscle is just a curve. So let's turn it back on, but I can make the radius narrower. So let's make it this narrow, then it's easier to see what the muscle is doing. Okay, the points are over there. So if I rotate this, I can see how the points behave in different postures. If you want to be more precise with this, you can actually plot the moment arms while constructing the model so that you can see the effect of changed moment arms. So quickly I will demonstrate this. So the selected joint is the ankle. We're interested in the Z joint degree of freedom, and we want to go from 0 degrees to maybe 90 degrees flexion just to see what the moment arm does. So we hit 90 degrees, we have the selected muscle, and then we hit compute length and moment arm. And we have generate plot selected, moment arm, etc. Boom. So now if we go over here, we'll see the ankle moment arm. This is quite useful, I think. While building the model, we see that in the fully extended posture, the moment arm is about 1.5 centimeters, and it goes up to a peak of about 2 centimeters and then down to 1.5, but it remains positive throughout the joint range of motion. So up till here, it's still got a flexing moment. You can imagine that if you are constructing your model, you might want to actually try to match data, match measurements of moment arms, and you can what you can then do is change the position of the points. Let's say I want this, I might want this point slightly higher, and then I can regenerate this plot by selecting the muscle and the joint, and then let's have it in view so we can see what happens, and then hit compute length the moment arm, and you'll see the moment arm is changed. So this is quite useful if you want to iterate and try to match actual measurements. So it's up to you, of course, to decide how accurate your moment arm needs to be and over what joint range it needs to be correct. You might want it, I'm going to hide this actually, we don't need to see this. It might actually, in some cases, be better for you to have wrapping, and I'm going to show you how to add wrapping next. We're going to do this with a gastrocnemius. If I now flex this joint, which I can just do by selecting the joint and rotating it, we see that this point should not have been parented to the thigh. It should probably have been parented to the shank. So what we can do is select that second point, and in the hook and in the modifier panel, the second point is, well, this is the first hook modifier, so this is for the first point, but we want the second point, and instead of having it parented to the thigh, we will parent it by hitting this eyedropper to the shank. Okay, so now if I flex, yeah, that looks like the behavior I was after. Maybe we can place this point a bit lower in that case. And maybe move it out to the side. There we go. But if we move the ankle, we now see that the muscle will move through the bones. That's not what we want. We want to add wrapping here. So in the wrapping panel, you can create wrapping geometry and you can assign parent bodies, and then you can assign wraps. I'm going to turn on parametric wraps. But let's create a wrapping cylinder. We're going to call this ankle next wrap R. Doesn't really matter what we call it. Create wrapping geometry. The geometry by default is added to the 3D cursor location, but of course we're going to modify this anyway. So once this geometry is created, first of all we want to position it where we need it. In this case we probably want it in exactly the same position as, or approximately the same position as the joint. So let's do that, and it's obviously much too large. So with the wrapping geometry selected, if you go to the modifier panel, again that's the wrench over here, you can change the radius and the height of the cylinder. So in this case, let's first change the height. This looks about as wide as it needs to be. Of course, it doesn't matter if it's wider. It does matter if it's too narrow. But the radius is obviously much too large. So we want to decrease the radius, and you can see that these steps are rather large. If we drag this and hit shift, we can change the radius more finely. So I'm going to put the radius at 3.5 for now. And so we now have our wrapping geometry approximately where we want it. It's not assigned to a parent body yet. So if I move this, you can see that the geometry stays in place, and actually one of the articular surfaces that we fit earlier is also still in place. So we can remove that later if we want to. But we can parent this, and we should, of course, parent this to a body. So let's parent this to the shank R body. So in the wrapping panel, we now see that we have the correct wrap selected and we have the correct body selected. Then we hit assign parent body. Now the wrap moves with the shank body, but it's still not assigned to a muscle. So the next thing we do is we select the muscle, we select the wrap, and we hit assign muscle wrap. And for this, I've selected parametric wraps, so I can demonstrate something in a bit. And it's assigned. Perfect. But this is obviously not the behavior that we want. So I'm not going to delve into the wrapping settings for this tutorial, but for the tutorial, if you want this to work correctly, we change the projection angle. We can either change the projection angle, or in this case, just hit flip wrap. But then it might not give might still flip once you flex it too much. But in this case, flip wrap works for me. You might also have to change instead the projection angle and then the index of the pre-wrapping point. This is all documented in the manual, and I'll be making a dedicated tutorial for the wrapping panel in the future where I dive into the nitty-gritty of it. I'm not going to add any distal muscles here because it's not necessary for this tutorial. Now, if we want to export this and want to make sure that then this joint remains locked, what we can do is go to the object data, to the custom properties of this joint, and in the coordinates, we delete the MTP angle R. So we select it and delete it. Now the joint has no coordinate, and that means it will be treated as a locked joint during model conversion. One useful feature while building your models might be the live length viewer. I'm going to collapse these panels for a second. You can view the length of any muscle in real time by selecting the muscle and then clicking this button. Then you see the length in meters over here. Now this is also a modifier, and I can change the position of this modifier if I like and make it slightly smaller or bigger. This is useful if you want to estimate contractile parameters based on the length of the muscle in different postures. So for instance, if I change the knee angle, you can see that this muscle is increasing in length. So you could use this to place your model in different positions and estimate the changes in length. I'm going to remove this modifier. If you can assign contractile parameters to all of your muscles if you like. You can, once again, selecting the muscle and going to Object Properties. Under Custom Properties, you can fill in an Fmax, an optimal fiber length, pennation angle, and tendon slack length. I assume that if you want to add more parameters that you can do this yourself for whatever simulation software you're interested in. The OpenSim conversion gives you some options like Vmax as well. This wraps up all that I wanted to show for the muscle creation. Let's quickly move on to adding contact spheres, and then we'll reflect the model, and then we will have a fully defined model. So contact spheres, you guessed it, are added in the contact sphere panel. So by now, you might actually have some intuition for how this might work. You hit Shift, right-click to place the 3D cursor wherever you want, and then type in the desired name. This is the second toe, because emus and other ratites lost their first toe, their big toe. So that we're going to call this toe tip to R. And then we hit Create Contact Sphere, and it's added to the toe tip. This is obviously not parented to anything yet, right? So, once again, you know how this works now. Select the contact sphere. You can't select the geometry. That won't work. If I try to assign this, it will tell me that I didn't select a target body. So, what we can do is, of course, parent it to bodies. So, I hit it, and now I forgot to select the contact sphere. So, again, select the contact sphere, assign parent body, done. You don't have to do this one by one, so I can add more contacts, create contact sphere, toe, tip, 4R, create contact sphere, and maybe one over here, heel, pad, R, create contact sphere. So I select all of these, select the desired target body, and then I hit assign parent body, and now all of these are parented. Since you can't do any simulations in MuSkeMo, I'm going to assume that you will assign your contact parameters for whatever simulation software you prefer, and that you will be able to do this in that software. The OpenSim conversion script that I made does give you the opportunity to change these parameters during model conversion. So now we have a fully defined right side of the model, and we would like to create a left side for everything as well. So this happens in the reflection panel. And it works, as I mentioned before, using the strings that you used in your naming conventions to create the bodies. You have to be very consistent in how you name all of your objects and use the same convention for either right or left sides. What we could have potentially done is create some parts on the right side, some part on the left side, and the panel will be able to deal with this. Now this panel is quite straightforward to use. You simply tell it which collection it should work on. For the bodies collection, the bodies aren't in their default collection name, so that's the body collection. So you just hit reflect unilateral bodies. And now all of the bodies on the right side are reflected to the left side. This would also work if we have local frames assigned, but I'm not going over local frames in this tutorial, but just rest assured that it would still work. What it doesn't do currently is reflect visual geometry. I don't have a button for this just yet. If you want it, let me know. I might add it, but it's actually quite easy to do this manually. You just select the objects that you might want to mirror. So in this case, all of these bone meshes, we hit Shift D. So now they're all duplicated. You can see here that they automatically get a new name, and it has to be unique. Blender can't have duplicate names in the scene. With these still selected, we hit Detach Visual Bone Geometry because they're all still attached to the right side bodies. Now, with all of these still selected, we hit Object, Mirror, Z Global, and there we go. Now we still, of course, want to give them meaningful names. So this should be a thigh LV2. Then again, we go through this, attach visual bone geometry, attach visual bone geometry, attach visual bone geometry, and attach. And now we're done. All of these visual geometries are parented to the correct bodies. Now we can go back to the reflection panel and go through the rest of this list. So we're not reflecting any frames because we didn't add any local reference frames today. Instead, we're going to reflect the unilateral joints. Boom. The entire left side is now correctly parented. We can do the same for contacts. Reflect unilateral contacts. Now we have contacts on the left side. And we can do the same for muscles. Perfect. Geometry objects are separate from muscles, so we have to reflect those separately as well. And once you do so, they automatically get assigned as well. It doesn't look symmetric because on this side we had manually changed the visualization radius. So if I remember correctly, the radius was 0.05 on this side, so we can change it to 0.05 on this side as well. And then you'll see that, yes, indeed, the muscle is perfectly symmetric. Now that's, of course, a visualization radius, so it doesn't matter for the behavior of the model. So now we have reflected all of the components that we've created to the left side. So now we have a fully defined model. You can, in principle, assign contractile properties to the muscles, and then the model will essentially be ready for simulations in whatever software you like. Once you're happy with the model and you would like to start exporting model components, you can go to the exporting panel. There you can select an export directory. This is strictly speaking only necessary if you want to export a geometry folder as well. I'm going to create a new directory and call this emu demo model. And then I'll hit select model export directory. Now you can see that it's filled into this box over here. And now we can just go through each of the sub panels and export whatever is listed in the sub panel. So all of these will work using the collection that your objects are placed in. At this point, it might be a good idea to double check that your collections only contain things that you want to export. So for instance, does your bodies collection, which is listed here, does your bodies collection only contain objects with the MuSkeMo type body? If there's anything else in there, it's just going to be ignored during export. So I'm going to just hit export, and then it pre-fills a name which I can change if I want, but you don't have to. And then you hit export bodies. If I now navigate to the export location, which is here, emu demo model, you'll see that a CSV file popped up. And this is what you get if you open the file. It's a CSV file that just lists all of the body data. Quite straightforward. And we can do the same for joints. It gave a warning, but you can ignore that because I'll be removing that after uploading this tutorial. We can do the same for all of the muscles. Export the wrapping objects. Export mesh inertial properties is essentially if you would like to export the inertial properties computed for these tissue outlines, so individually, not as combined rigid bodies. It might be useful, then you use this option. Exporting reference frames obviously only makes sense if you create reference frames, which we didn't in this tutorial. We didn't create any landmarks, but we can export contact locations. And we can export a visual geometry folder. This is the only one that actually requires assigning a model export directory. And you will see that they have been automatically created in a subdirectory. Here we go. And obviously we imported them from this state, so we're essentially redoing the export, except for the thigh L, of course, which did not exist in our imported data. And lastly, there are some options. You can change the delimiter if you like. You can change how many significant digits you export. By default, MuSkeMo assumes you want 4 significant digits. You can increase this if you like. You can also change the export file type. It's possible to change this to TXT or JSON, for instance. And I think this about wraps up this tutorial. So in future tutorials, I will delve into some of the individual panels in more detail. I'll also show you how to use the conversion scripts, which use the CSVs as an input. And I'll probably make a dedicated tutorial for making visualizations in MuSkeMo, because this, of course, combines MuSkeMo specific features and just general Blender rendering tips. I hope this tutorial has been useful. Feel free to leave any comments if something is unclear, and I'll try to resolve them. Thanks a lot, and happy model building.